you have less, and then the negative is like you have more than you need. But especially when it's a structure like just the cyclohexanes and stuff, I don't understand the partial charges when you're doing the contributors, and I don't understand the placement and how we're like determining the charges on all of these basically.
Yeah, so resonance, yes, absolutely. Resonance structures is one of those things that you have to get comfortable with. You're going to see it come up again and again, just like energy diagrams. If you don't love energy diagrams, learn to love them and learn to draw them because they are not going away. Resonance will not go away either. And especially if you do OCOM 2 or, just continue on in that fashion. So, yes. Is there let me see. I went through and I kind of picked out some good spots from the book that I thought were pretty important. Let's see, this is too far ahead. Okay, so as far as, so you want to know how you move, say, a pair of electrons around a structure and then create this, what I think you're talking about is over here, how we have these kind of dotted lines, and then we have like our partial charges. And then for example, you would see kind of stuff like this, where you'd have your delta, right? Like usually it'd be like delta positive, delta negative, right here. How you have these, let me make this a little bit smaller. How you have these dotted lines with your delta positives here. Is that what you're talking about?
Yeah, those are like perfect examples of what exactly what I'm talking about.
Yeah, okay, perfect. Okay, no problem. Yeah, absolutely. So, we can, some of the biggest things to remember when you're doing resonance is you cannot do resonance on an sp3 hybridized atom. So for example, this is an sp3, and you guys all, remember, I'm assuming, the difference. Oh, I'm sorry, Sarah, I did just see your text in the chat. Yeah, please definitely feel free to like unmute because I'll forget to read the chat. So if I haven't responded to your message in a while, just unmute. And I am also recording, just so everybody knows, but they can only see my screen. So anyway, so hybridization, I'm sure you guys obviously just all got tested on it, so I'm sure you haven't forgotten too much about hybridization. So this is your sp3 hybridized. You can't do resonance on an sp3. It's already filled. But you can basically everything else, right? So when you're moving electrons, let me find a curved arrow pushing example. So this one. So as we see here, we have three substituents, essentially, three electron domains. So this is sp2. This is also sp2, all the way across, right? I'm not going to go through all of them, but they're all obviously sp2. So we can move the electron. So in this example, we're just talking about a radical, which is a single electron. It's not a pair, but it will work essentially the same way. The only difference is what you'll see coming out on the other side. So in this example, these curved arrow pushings, right? So we have this radical, we check, so this radical is on this carbon here. So we go, you're not going to go to a hydrogen, just FYI, because hydrogen can only make one bond. So hydrogen, you'll never see a double bond to a hydrogen. So just forget about hydrogens, pretend they don't exist, and they're just kind of there to help support. So we'll do and remember that when you're just dealing with a radical, you just do a one-sided arrow, as opposed to when you have a pair of electrons, a pair of non-bonding electrons, you do the double-headed arrow. So in this case, right, so we check from this carbon, it's only attached to one other non-hydrogen molecule, and we check that and we see that it's sp2 hybridized. Perfect, we can move it. So just as these arrows kind of show, is that we move this radical over here. And I'm sorry, let me specify also that if you don't have like another, in this example, like a double bond, if you don't like anything other than a single bond, basically with a radical, you're not going to be able to move it because it's just a single electron, and electrons bond to an atom bonds to another atom in a pair. So you have to be able to get the other electron somewhere, right? And there's two different kinds, right? This is particularly radical curved arrow pushings, right? And so we see that, we use one electron from this, and then you have to push the other electron to the next atom. So the atom, because your single electron isn't going to sit here in this bond area. It's going to go and sit on where the protons are, essentially, right? And we go across that way, and we can make our way down, right? And we see when we do that, we note that, and like as we make our way down, right, we have a radical that sits on this one, a radical sits on this one, and a radical that sits on this one. And we can see that here. See here, here, and here. So those are where your delta energy is going to be, right? And then wherever that you had, so a great trick to look at is overall build your skeleton structure first. So in this case, our skeleton structure would be everything. Let me do it in a color that's gonna like stick out. I'm doing this bright green color, right? So our skeleton structure is here. I'm just gonna draw it over the atoms because you guys obviously know, right? And then to all of our hydrogens. So that's your skeleton structure. So that's what you'll build first. And you'll note that we have our skeleton structure here. And this applies across the board, no matter what kind of hybridization you're doing, or curved arrow pushing, and it's all going to apply the same way. And then you just go through and you say, okay, there was a double bond across this part of the skeleton and this part of the skeleton. Oops. And then you go over here and you see that there is a double bond still on this part of the skeleton, but now also on this part. And then we see again now this one and still this one. And so that's how we get these dotted lines all the way across the board, because at some point there was a double bond in that area. And then wherever for these, in the case of a radical, you would just do your delta radical on each of the atoms that held a radical at one point. Okay, so that's how that works for radicals, and it's literally the exact same thing, except you get to move bonds around rather than moving a single electron. And so we'll use this for an example. So this is our main structure here, right? What they're asking. So there's a couple of ways that you can do it. So in this case, this would be, right? You could say over here, right? You have an sp3 hybridized, you couldn't do it. But because this has a formal charge, you can then move your electrons over one. And so when we move them over one, now we have our bond here, and we have to move that because this atom right here had a double bond, right? So it was sp2 hybridized, and now it's no longer sp2 hybridized. We're missing a pair of electrons because we took them and put them here, right? And so that's why we end up with our positive formal charge over here, okay? And it's good to note that you're not gonna see this happen. You're not gonna see this part happen because this is so unstable and unreactive that it's what they call unreasonable. And so you're just literally almost never going to see that. So it would not be, even though it would be correct to say that you could move a bond here and that it would go here and then it would kick your electron pair over onto this corner. It is correct to say that, but due to what it creates on this end, it's what we call unreasonable and would just basically never happen. So again, so this is our final structure here, right? After our resonance. So we go back and we draw our skeleton and we decide. So we had the hexane group and then we had the ethyl group. And also the similarities between these two groups is this double bond, because we decided that wasn't going to happen. So we can put our double bond here. not what a double bond looks like, but you know what I mean. Anyway, whatever, you get the point. And so that's our skeletal structure. And then we say, okay, there were double bonds here, and there were double bonds here, and there were formal charges on this carbon. So we would say this was a delta positive because it's a positive formal charge. And there was a formal charge on this carbon. So it becomes a delta positive as well. And that's how we end up with this structure. And, these are the reactive areas because obviously anything with a formal charge is going to react with another molecule or whatever it is that we're trying to do with that. So that's kind of the basis of how we, these are simple examples of how we move electrons around to create resonance and how we have partial charges. Does that kind of lay a foundation a little bit? Do you have questions about those two examples before we start building onto that? Anybody have any questions? Not just Sarah.
So, I noticed for the ring, how do we differentiate, like, because I saw on like either problem 5 for like resonance contributors, they had like a 1/3, 1/3, 1/3, like equally distributed, but over here is the delta positives distributed. So, yeah, that's
We
something
could,
that I'm kind of confused about.
yeah, sure. And so that it's just not really saying it. We could say 1/2 because there's two, you know.
Oh,
And
okay.
yeah, so it's just not really saying it. And in this one, we could say a third, a third, a third, because they're sharing it, over here. There's 3 delta positives. So you could, it's just not noted on here. But you know, it's reasonable to say that. She'll tell you when she wants you to write like this versus just that. If she hasn't changed her exams too much. So yeah, it's perfectly reasonable to say that though.
Oh, okay. Thank you.
Yeah, no problem. How's everybody feeling about these 2 resonance structures so far?
Yeah, I'm good with this stuff. I
Perfect.
have questions with resonance, but not on this specifically. So I guess if you want to finish this for the other people, if they still have
Yeah, no,
questions.
whatever. It's totally up to you guys. Like I can go through, I kind of just went through the book and pulled out all the pieces that are good to remember for your exam and just conceptually to build as we go. So it doesn't have to be I thought I added problems too. Or
I
maybe I
have
didn't add them
like
till the end. But yeah, go
I'm
ahead.
if I can go, I'm specifically struggling with the homolytic bond dissociation homework problems. Can you just like look at one of them and maybe
Yeah.
explain it to me?
Yeah, totally.
Okay,
Which one? Let me pull it up on
number
my screen.
10, the last one.
Yeah, hang on. Let me reload this.
And then once you get there, I have like a specific thing for this problem that I'm clearly not understanding because it messed up the resonance structures.
Yeah, no worries. Okay. So rank 3 indicated correct? That's the one. I'm gonna add it to my,
Oh,
let me
sorry,
look.
I'm looking at it in my notes. I don't know. I gotta pull it up on the computer.
No, you're fine, you're fine. Let me just add it to this real quick so that I can, whoops. Is it
Yeah, rank the 3 indicated CH bonds.
cool? It should
Yeah,
get
so
bigger. I it didn't, but that's okay. Okay.
so I understand the gist of, breaking the bond, having 2 single-headed arrows moving the electrons. Like I get that.
Mm-hmm.
But I'm not understanding, in the resonance structures that they did in the answer key,
Mm-hmm.
you know where the bond is, the carbon that's in the CH bond, is
Mm-hmm.
that carbon still sp3 hybridized? This is why I asked, because so when you look at the resonance structures that they drew,
Mm-hmm.
they like moved the double bond and they moved the like radical onto that carbon that's now freed, if you will, given that we've broken the bond to hydrogen. But
Mm-hmm.
I thought that that carbon was sp3 hybridized. So either I'm wrong in thinking that it's sp3 hybridized, or I'm not sure why you can use that in resonance.
Can you
If
tell
you
me,
can like,
can you tell me which A, B, or C that you're specifically talking about, just so I can.
yeah, let me just look at it. Okay, yeah. So like, for the bond at B,
Mm-hmm. Yeah, it is
isn't that
SP.
isn't that
It,
sp3 hybridized?
it is. It is.
So then,
It's a third, but it's sp3 hybridized because it's still connected to a hydrogen. Once you break that, now it's an sp2 with a radical.
okay, see, that's what I
So it
wasn't
becomes a third
understanding.
degree radical. Yeah. So yes, in this case, you're absolutely right. B, which is this carbon right here, is sp3. But once you break it, and I'm just gonna draw just this section here, right?
Mhm.
So once you break it, then this becomes an sp2, right? This is
Mm,
that carbon right here. So now this is an sp2 carbon little hybridized, right?
yeah.
And this radical becomes a third degree radical because it's connected to, right, quote unquote, excuse me,
Mm-hmm.
three different substituents. 1, 2, 3.
Okay, so yeah, so that's where I was confused because I thought I looked at the original structure and I said it's sp3, it
Mm-hmm.
can't participate in resonance,
You're
but
right.
that's not.
sp3 can't. No, you're right. sp3 can't. But as soon as you break that bond, it's no longer sp3 hybridized
I
because
got it. I see.
yeah, we've broken, erased, gotten rid of, right, that fourth leg.
Mm,
Does that make sense?
yeah. And then also, still on this problem though,
Yeah.
like I was just struggling with just I guess we can stay at B,
Yeah,
at the
please.
resonance B. Like, can you explain what the rules are that govern like where it's reasonable for the radical to be? Because I don't really know how like the radical part is just like moving across the molecule. Because like I thought when you do resonance, um, like when you're doing bonds, for example, you move a double bond, like it moves one place at a time. So
Yeah,
how is it
radicals
that
only
like,
move. Yeah. So that's what I was saying up here is I'm gonna just sneak back up to the notes that I was just making before, right? Is up here. Remember that let me just erase all my nonsense, right? Let me just get rid of some of this stuff. So we've got this radical here. Let me pick a color you can see. So you've got this radical here, right? But remember that a radical is one electron and bonds want two.
Mhm.
Okay. So when we do, one electron has that single headed arrow pushing, right? Whereas if we had a pair of non-bonding electrons, or if we had a double bond, we would use a double-headed arrow to denote that, right? So this
Yeah,
is,
yeah.
say this is on a different structure, right? So now when we're talking about resonance, we have to look at, this is the radical is right next to, I hate when it does that, right? So this radical is right next to the molecule, or rather the atom, the protons that it's connected to, right? That it's attracted to, right? And so when we want to move it, we have to look at, remember, hydrogens don't count. They can only make single bonds. That's it. There's no resonance to hydrogens, right? So we have to look at the following atom. In this structure, the following atom is a carbon. Now,
Right.
if this structure was, say, this, which, you know, just bear with me. Obviously, this is breaking this carbon, right? Breaks, well, there we go. Okay, so let's just say this. Now we've got a methyl on this end, right? So if we had this structure, this bad boy right here isn't going anywhere, because this radical isn't going anywhere, because one comes in and there's nowhere else on this structure for another electron to meet it. So
Right.
it's going to sit here on this carbon, right? But
Okay.
that's why sp3 can't participate in resonance, because all of its other electrons here, oops, sorry, here, and here, they're already being used. They're already being taken up. There's no, you're not breaking that sigma bond. It's not, because what you would do is you would cleave this to create two separate molecules, right? And that's
Right.
just not going to happen. So in this case, the next atom over to where you want to move your radical has to be sp2 hybridized at the least, you know,
Yeah.
sp short,
Yeah.
right? So that you
Uh-huh.
can take, so each of these bonds, so think of it like this, each of these lines has two electrons that are connected together to create, not
Yeah.
literally, right? Like I'm
Yeah.
really
No, I get
oversimplifying
you.
this, but yeah, okay.
Yeah.
So you would move this radical in here, and one of these radicals, one of these electrons from this bond has to come in to join it. And so once it does that, now we have this bond here. So here's this radical. It's not a great color. Here's this radical. Okay. So
Mhm.
stupid. And here's one of the electrons from that to create this other pi bond. And then this radical single electron hops on here, because it
Yeah.
can't go to another, it's radicals have to move like one little space at a time. Double bonds, or rather paired electrons, can jump entire
Yeah.
they can jump entire bonds. So we
But
don't have
that's
to
why
put,
yeah. Oh, sorry.
no, you're fine, go.
But that's why I'm confused on B, because like it's not moving one space at a time. It's moving across the entire molecule, right? I mean, like, cause look, it's in like the top corner. I mean, it's like north basically, and then it's moving to southeast.
Okay.
How?
Okay, so yes, because they didn't do the curved arrow pushings to show you, which I will do. So okay, so we're gonna break this. What we end up with, whatever. And what we end up with is this. With me
Uh-huh.
so far? Okay,
Yep.
perfect. So then we're gonna take this radical and put it right here. And we're gonna take half of this bond and put it right here.
Oh, I see it.
Yep, yep.
Yeah, I
So
see.
yep. So then what we get, just for completeness, right? Whoops. We get this. And then we get a radical. Oh,
Yeah.
I didn't put this guy right here. Perfect. Does that make sense? So it's not
Yeah.
actually this radical that's jumping all the way over here. This one is one electron from this bond that you broke that's no longer here.
Yeah, no, I totally see it now. And then I don't understand for A, um, so why can't you draw a resonance structure that has the double bond, like in the basically the southeast corner? Like I drew like a double bond down there. Like I don't, maybe I just messed
Over
it up. I
here,
don't know.
like you would put a double
Like,
bond here, or
yeah, like between the ring. Oh, because then I'm breaking octet. That's why.
mm-hmm. Yeah.
Yeah, okay. No, wait, actually, no, wait. For part C. Oh, yeah, yeah, okay, then you can. For part C, you can. Oh, okay. Yeah, I just messed it up, I think.
It's all
Okay,
good.
never mind.
Yeah, no worries. Yeah, so for A, the radical, it can't, so once you break this, it's the one thing about drawing structures, you have to do it like a million times, right? So it can't go this way because this is an sp3 hybrid.
SP3.
Exactly, this is
Yeah.
an sp3, and it can't go this way because there's already a bond there. There's already a double bond there, so it can't. There's no, you can't make a triple bond with it. So it can't
Mm-hmm.
go anywhere. It just sits there, and it's an
Got it.
sp2. I mean an sp2. I'm sorry, a second degree radical. Yes. You don't have to raise your hand. You can just hop on.
Oh, okay. So, what you said about like doing like homolytic bond association for A, just like question to like clarify, does that make like a secondary because there's like two like there's two like domains attached because
Yeah,
I'm
like
I'm looking,
a second degree radical.
yeah, second degree radical, would that
Yeah,
be it?
I see
And
that it doesn't say it in the, it doesn't say it in the homework answer, but that might just be because they are like the question, yes, the short answer is yes, it's still a second degree radical. I think the reason why it's not in the answer in the homework site is because the question is asking to rank the order of increasing bond association, and degree of your radical doesn't matter because A will be the highest because it's not stabilized by resonance. So regardless of um what the degree is, it's going to be the highest anyway because it can't, it's not stabilized by resonance, whereas the other two are stabilized by resonance, and that's when it will matter if like what degree your radical is. Does that make sense?
um can you go over with that with me one more time?
Yeah, okay, so for this is my resonant, or my quote resonance, right? But there is no resonance. This is what it would look like if I were to break A. If I were to break this, if I was to do this and I was to do this, I would get this structure right here. And this is my radical. It like thinks I want to erase it, but I don't. Okay, and this is my radical. And yes, I wrote that it's second degree, right? But it doesn't particularly matter because there's just no resonance. And as I denoted here, it can't go to the left because it's an sp3, and it can't go to the right because there's already a double bond. It's already taken up space. So it will just sit here. So there is no resonance. No res. Okay. So if a radical has no resonance, then it will be the highest energetic, it will have the highest bond association energy because it's not stabilized by resonance.
Mm-hmm. So I'm
Okay.
kind of, yeah.
Yeah.
So I'm kind of like noticing a pattern that like the more, oh, like forgive me if I'm wrong,
No, you're
but
fine.
the more like resonance structures or resonance contributors that it has, the more stable it will be. So it will have
Yeah.
a higher bond association energy.
Um, so the more stable, so Yes and no, right? So a lot of it's going to depend on like here, right? Where are you starting from? Are you starting, um are all of your structures, like in this case, they're all sp3 hybridized, or sp3 hybridized. So like as you go up, you have your different, right, degrees of radicals, and that's why like your bond dissociation gets bigger, right? Versus like a third degree radical will, because there's more substituents to it. So a radical, like it has to do with what it's connected to. So for example, the radical will be here and it's first degree, right? For this one, the radical will be here and it would be a second degree radical. For this one, it would be here, right? And it would be a third degree radical, right? But so you could say that this one would have the highest bond association energy because it has the furthest to travel, right? First degree radical is higher than third degree radical, right? But because this one isn't stabilized by resonance, there's no resonance, it's the highest, right? There's nowhere for this radical to go to stabilize it. So even though this is a second degree radical, because there's no resonance, this one is going to be the highest. Now, once you get to here, to these two, C and B, then you're going to have to look at your resonance structures as well, right? And so this one has two resonance structures that has a first degree and then a second degree because it'll move here. And this one has a third degree and then another third degree because it'll move here, right? And so that's why this one will be the lowest. B would be the lowest because it's two third degree radicals. Now, if you're dealing with structures that aren't radicals, like, where do I have something? Like these, right? Then yeah, definitely the more structures, the more resonant structures you have, the more stable your electrons are going to be. So yes, typically that would be the case because they're not going to want to, they're happy. If they're stable, they're happy. The more people there are around them, the happier they are, if you think of people as molecule or atoms. Does that make
Oh,
sense?
yeah, it makes sense now. Thank you.
Yeah, you're welcome for sure. Perfect. Was it Sarah? Were you asking questions about this structure? Were you the one who originally?
Oh wait, that was me.
Oh, it was you. Okay, sorry. I couldn't remember who it was. Is there another part of this that I can help explain to you?
I think I'm good on 10. I have a lot of questions, but I don't want to step on anyone's toes if someone else wants to go because I know I already got one in.
For sure. Well, does anybody want to
I have a
hop in?
question.
Yeah.
So for the homework, I was just had a question for the partial positives. So I noticed on one of the homework assignments, what was it? It was the resonant contributors.
Uh-huh.
So I just had a question on when we put the partial positives, because on question number 10, it did do like 1/3 partial positive, but then when I did number 12, it didn't require me to put like the 1/3 partial positive. So I was just wondering like when do we add like the 1/3 or like the 1/2?
Sure. Yeah. We went over that just a little bit before you got here too. You were not the only
Oh,
one
okay.
who was
If
asking.
we went over, I could just look
Oh
back at the
no. I can explain it to you. It's not a big deal. I'm not sure what the problem is. Is it in the resonance contributors one in particular? Typically, it's going to ask you what. So indicate partial positives, and then you said 12. Indicate that carry partial using the hybrid. Yeah. So in 10, it's 9 times out of 10, it's going to be like what it's actually asking you. So 10 says indicate the partial charges. So it's going to ask you in particular, right? Like this one. It's going to ask, like, it wants to know, like, what are the partial charges, right? Versus in 12, it just says, indicate the partial charges as using the delta symbol. So it's not actually asking you what they are. So it's just saying like what, like just
Oh,
tell me
okay,
like
okay.
which atom has, right, like this, like they want to know like, does this have a partial, does this have a partial, does that have a partial, right? And so they're just saying like just denote it with a delta, positive or negative, whatever it is. But it is fair to say like this, right? Same thing, like they're just saying, but it's fair to say that this is 1/2 and 1/2 because there's two that are sharing, right? Versus like over here we have three that are sharing, right? And so it's, yeah, it's really going to depend on the question. And typically she will ask you specifically to, like, she will say like, what is, include the, ratio or what, I forget exactly how she
Okay, so
asks,
it's just the
but
wording of the question.
yeah, exactly. Yeah, there's
Okay.
no, yeah. Yep.
Okay, okay. That was it. Thank you so much.
Yeah, of course, no problem. What else y'all have?
If no one else has one, I have one.
Sure.
Yeah, so can I just like read you like the structure? Because I don't actually know what questions these are. I don't know what the number is.
Yeah.
Um, yeah, so it was basically oh wait, no, I think it was from the notes, but I don't know, whatever. It was just like what is this? 1, 2, 3, 4, 5. A hexane ring, and then it had like on one of the corners, it had a positive like charge in a circle. Yeah, like on the top. Yeah, okay, that's fine. It doesn't matter which one. And I just didn't understand like what that meant. Because doesn't
Means
that
you can put an
corner,
electron there.
it just means that there's like another electron.
No, it means you can put some there. It means it just means it has a positive charge, missing electrons, so to speak, right? Anytime that you have a positive charge, it means that you have less electrons than that particular atom likes. Or if you have a negative charge, it means you have more electrons than, I don't like to say what it likes, but because oxygen loves, like, it's highly electronegative, it can carry electrons very easily, right? But like a carbon,
But
for
then
example, right? Carbon's happy. Yeah, go ahead. No, go.
but then how is it satisfying octet? That's what I'm confused about.
Yeah, so like technically, right, it's not, and that's why you're putting a positive there. The octet is so that you know how many electrons it needs to be happy, and if it's not happy because it has too little, it would have a positive, or if it's not happy because it has too many, happy, right? Like, you get what I'm saying though.
So
Octet rule.
like so
Then it would
like
have a
it
negative charge.
so like it because the reason I'm confused is because like you know how normally it would have two hydrogens attached to it to achieve the octet.
Yep.
Well, if you took, say it only had one attached to it, then isn't it missing two electrons? Like how is it how can it only be deficient one? Because a bond is two.
The positive charge is not, it's a +1, but it's because it's a quote missing. It's not a radical. Radicals will be denoted with a dot. So think of electrons, think of charges as always meaning two electrons, unless you see a dot. But if you see a dot, you're not going to see a positive or a negative. You're going to see a dot because it's different, right? So when you see a positive or a negative, it means it's because it's too many or too few, right? Too many or few,
Oh, I
right?
thought it meant one. Oh, okay, that makes more sense.
The charge, right? The formal charge might be +1 or -1, but this actually means 2 electrons
I see. Okay.
because you have to have 2 electrons to make a bond,
Right. That
whatever it
yeah,
is.
that's
So this would
why
be
I was
6
confused.
electrons right here. Yeah, so this, I started to draw the structure out just to give you an idea. And this is why we kind of go over this stuff in the beginning. So, right, so carbon wants 4, nitrogen wants 5. So 1, 2, 3, 4, 5. Whoops. Other way around. Wants 4, has 5, -1, negative charge, right? This one wants 5, has 1, 2, 3, 4, 5, 0, neutral. This one wants 5, has 1, 2, 3, 4, +1. So we have the positive formal charge. Does that make sense?
Okay. Yeah. And just kind of a related question.
Yeah.
The reason I'm trying to get at this is like so whatever atom a radical is on,
Yep.
how does that influence the hybridization? Like, you know, when we're trying to figure out if something has resonance. So if you have a
Yep.
structure and like on the corner of like a hexane or whatever, there's a radical, then yeah. So like at that corner in the southeast, yeah. Is that carbon still going to be sp3?
So this carbon, that's a great question. So this carbon was never sp3 hybridized in the first place.
Okay, can you explain how you know?
So this is the original structure. This is the original structure.
Uh, okay. Yeah, I was looking at the one all the way to the left.
Yep. Yeah, that's because this is resonant. See how we have these arrows and
Mm-hmm.
then these brackets denote our resonant structure. So in this case, we're going this way, we're breaking the HA bond. And if we go this way, we're breaking the HB bond. I want to make sure I was saying that correct. So, so in our original molecule, this one's sp3, this one's sp3, and this one is sp3. Let's see, that's sp2, that's sp2. This is sp3. And then these are 2 and 2. Okay, perfect. So our sp3 hybridized originally were these. Okay. So, but remember that when we break this bond, it means that it's no longer sp3 hybridized.
Mm-hmm.
Okay. We do have a hydrogen here as well. It's not there because we don't care about it right now. So, so we still have this hydrogen here, but we broke this bond, which means that we are now sp2 hybridized. Now notice that the resonant structure does not go this way. It can't go this way because these atoms are all sp3 hybridized. There's also a hydrogen here, right? Just for sakes, right?
Yeah. Yeah.
So
No,
it
I
doesn't go
get
that
it.
way.
Yeah.
Yeah.
Yeah. No, that thing you explained to me is very helpful because I
Cool.
was definitely seeing that wrong.
Yeah, no worries. And it's the same thing this way, right? Like this is sp3 until we break this bond, but these
Mhm.
are still all sp3 hybridized. All 3 of these are still sp3 hybridized, and so hence why our resonance jumps this way,
So
right?
would there be a radical on an original structure?
It depends. There might be. There might be.
And
As
then how would you know the hybridization in that case?
well, it'd be like for example, let's take this. Let's take this exact same structure. We'll put a radical here, right? And we'll put a double
Mhm.
bond there, maybe a double bond here, right? So we know that there's always a hydrogen. There'll be a hydrogen here. 1, 2, 3, 4. 1, 2, 3, 4, right? 1, 2, 3, 4.
Yeah, how do you know that there's not 2 hydrogens on the carbon with the radical?
There can't be. There's a radical there.
Yeah, but then
You
even
still
so with
can't. You can't, because carbon can't hold more than 4. Carbon's 4. That's it. So if we want to put a radical on there, we can't do that, because that's now 4.5.
okay, when
Half
can
is
you
4.
yeah, when can you break the octet? Because in some questions, this
Yeah,
is like
there's some certain molecules, right? Like boron, I forget, beryllium, like oxygen loves to hold on to. So it depends on your oxygen loves to be negative. Like all day long, oxygen will do this. Oxygen's totally happy doing that. It will do it all day long. Technically, like broken, right? Well, actually, well, no, you haven't broken your octet. This is still 8, right? But you have more than what like oxygen would initially like, but it's happy to sit at this structure. Like carbon, it will not happen. It's not going to happen. Nitrogen, you can have more or less, right? Like nitrogen, because of its electronegativity. I don't know where I just had my structure that I drew, but anyway, somewhere here. Oh, it's down here. Nitrogen will happily have more or less, and it's cool. And carbon will too, but carbon cannot hold. Carbon is specifically an sp3, like its tops 4 bonds, and I put
okay.
all the way up here somewhere in the notes. Oh, here, right? So here's your rules, right, with your molecule. So boron only has 3, right? So some of these will, here, 3 or 5 violates the octet rule. Phosphorus and sulfur, right? So some will have more, some will have less, but carbon only ever 4. It only ever have
Okay.
4. Yeah, that's like,
Thank you.
yeah,
Thank you.
yeah, of course, yeah. And you don't have to know all the little like, that's the thing that's kind of nice. Where were we? That's the thing that's kind of nice about organic chemistry, is you deal with like 10 or 12 atoms. You don't have to know too much. So just know that carbon is only ever going to be 4. So yeah, so that's how I would know that. What else? Let me see. How are you guys about like your bond association? See, we went through resonance. We did a little bit of the bond association. Let's see what else we have here. Oh, nomenclature. How you guys doing with your nomenclature? I'll just like scroll through some of the stuff I have, and you guys can tell me if you have questions on it, unless you have specific questions, and we can of course cover that. But nomenclature, some of like the common ones that you're gonna see obviously are gonna be like your methyls, your ethyls, your propyls. You'll see a bit of these. ISO, just it just means this like branching situation here, right? What else?
I mean, oh, sorry. I
No,
have
go ahead.
more specific questions. I just
Please.
didn't want to, like, if no one else has any, I do. So I
Yeah.
don't mind going.
Yeah, no, I don't mind, whatever you guys want to do, like hop in, Danielle, Nicole, Sarah, if you guys have specific questions, please don't be shy, and I guess until somebody else says something or you run out of material, then we'll, so what tell me, what else? What do you want to know?
It's the same topic. It's
Yeah, no, that's fine.
number 9 instead of number 10.
All right, let me see. Let me pull it up. Yeah, resonance is a tough one sometimes. It really can be. And then the cyclical structures. Let me see. I'm trying to find. Was it homolytic bond association? No,
Yep,
what was it? Oh, it was the one. Okay.
that is the one.
All right.
Yeah,
So what number is it? There's no
it's
9.
9. Yeah.
No, there's just no 9. It only goes to 8, so maybe it's not that one.
Oh, I thought it was 1 through 10. It's like more homolytic bond dissociation, number
Okay, let
9.
me look. Homolytic bond. Let me see. Bonding basics part 1, alkanes.
It's in this week's content in the part 1. It's like the second to last topic. It's right next to the like resonance, the like minor resonance thing.
Resonance. Oh, more. There we go. Okay. Jeez. Okay. Sorry about that. Okay. 9. Let's see what
Yeah.
this says. Yeah. Okay. So let
It's like the
me.
same thing as the last, trying to figure out like uh, the like
Yeah.
now it's carbon bonds.
Hang on 1 second. I'm just gonna add it.
We're in the homework problems for the person who just asked in the chat.
Yes. Yeah. My give it a second. It's gonna update. I have stuff from the gap notes in my presentation here, but it will also. There we go. Give it a second. But I'm pulling questions from the homework site. Thank you. Come on now. There we go. A minute. Okay. What do you want to know?
Yeah, so for this example, I just didn't know that, like, I thought somewhere in the lecture video, maybe I was just hearing things or could have imagined it, I don't know, but I thought like when you have a ring, you can't, or like it's difficult to break the bond that's like the backbone of the ring. And for this question, all or the first and the third resonance structures were like breaking the
Mm,
bond that was the ring, and I just didn't understand like how you can do that.
mm, good question. Okay, let me. Give the product and draw the curved arrow pushing that describe homolytic bond cleavage. Okay, what's the original structure? Oh, it's specifically asking you to break that bond. That's why.
Yeah, and I know, like, and that like surprised me because
You're funny.
I thought one of the professors in the video said that like you don't do that, but maybe I heard it wrong or understood it wrong. I don't
No, I
know.
mean you wouldn't. You wouldn't. Like if you had. All right. There are plenty of things where we do break rings, right? There's plenty of reactions that you will come to understand where you do break rings. But probably what he's saying, I'm assuming it was Dr. Gould, but maybe it was somebody else. I'm just going to draw a similar structure. Let's put, let me see, I don't have to do all this. Let's just put a radical right here. And let's put, you know, something here, whatever. It doesn't really matter. What he's, or whoever is probably saying, let me just get rid of this, is you wouldn't do this to get right, like that's what they're saying. To get whoops, to get resonance, to get resonance, you're not going to you're not going to break a sigma bond, right? To get that.
Okay.
Yeah, but in this case, it's specifically asking you to break this bond here in green. right?
Yeah.
To get your radicals. And the reason why this, you know, might work or like would be halfway decent to do, I'm just gonna erase this so I have some space, is because what you end up with, oops, I just did that. Two tertiary, right? You have two like pretty stable radicals, tertiary radicals. So even without resonance, this is a pretty, he's happy to chill there for a bit.
Yeah, is when you're looking at these questions for the homolytic bond association and like the bond association energy, this
Yep.
is just a detail I don't remember, but like how do you know whether the hybridization like SP versus SP2, SP3 trumps if there's resonance versus trumping, looking at the radical and seeing if it's primary, secondary, or tertiary to figure out the relative energy. Which one is like the best indicator in those three?
Sure. And Nikolai, saw your question about nomenclature, and we will get to that. So as far as like, so like in this case, right, we have, these are SP3s. Both of these are SP3s. This, it would be broken here, so we're worried about this guy right here. But this is also an SP3, and this bond we're attached to here and here, so this is an SP3 because we have two hydrogens. 1, 2, 3, 4, and this is an SP2, right? So overall our product, right? So a lot of it has to do with like your, or rather your reactants, right? So where are your reactants at and where are your products at? And so if your reactants are generally all the same, right? So let's just ignore this one for a second, but you've got SP3, 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 then all of your reactants are the same. So they're all going to be at the same level, right? So then you want to worry about, okay, well, what would your radical be? Well, this radical would be a first degree radical. This radical would be a first degree radical, and this radical would be a third degree radical, right? So, and in this case, this one would also be a first degree radical, right? But so you would say that this one for sure is going to be the most stable because they're all SP3, right? And then you have first degree versus third degree. As far as like being able to say, a lot of the times you're gonna have something where it's like you have something that's SP3 and first degree, something that's SP3 and third degree, something that's SP2 and second degree, something that's SP2 and first degree. And so you'll be able, this is what you're talking about, right? Like, so how would we decide between this one or this one, correct?
Yeah,
Like
a
what
question
would
like
be,
yeah,
yeah.
yeah,
Yeah,
like
go ahead.
which is more important between all those three though? Like I don't like in questions in the homework, it would say like, oh, if there's sp2 atoms, then they're like the bond is stronger essentially than if it was an sp3, like, and I get that.
Yes.
But then in the same question, because they would give different structures and be like, rank them. And then another thing you had to look at was, do they have resonance? So is resonance more important than the hybridization? Or
Well, okay, so here's the thing. If we go back to our reaction coordinate, oh gosh, please don't judge me for this, right? SP, SP2, SP3. SP is the most stable, right? You guys learned this last week. Okay. For radicals, once they come out of it, let's just say reactants, this is our products. Our products are all the same, right? We just wanted to know like what was our dissociation for each of these, right? So for this one, radicals, right? Our reactants are all the same, our products are different. Then you have methyl up here. Me, whoops, Me, right? So if your reactants are the same, but your products are different, right? You have this whole kind of, you get it, right? Like, so if you, and then if you have resonance, right, they're going to be more stable than, you know, if it's a
Yeah.
third degree period versus third degree with resonance, obviously the one with resonance is going to be the most stable, right? So when you're looking at this is what I used to do, right? This is what I would draw on my, this is sp3, and this is sp2. Oh, whoops, other way around. Let me erase this. Sorry about that. sp2, sp3, right? First degree. Backwards again. Third degree, second degree, first degree, methyl. So this is how I would draw it on my exams or draw it in my notes to remind myself about like, these are your reactants and these are your products. So what is it that you're comparing? I will say that like, there's a lot of nuances, a lot of stuff that you're not necessarily going to learn about. There's like so much, this is like organic chemistry 1, you know, of like, and I'm not saying that as in like, oh, you know, it's no big deal, but it's like, we're just scratching the surface about a lot of different topics. And so let me just put to rest your worry that like, she's going to be like, okay, so you have an SP this and an SP2 that and an SP3 this that all have these ones and like decide which one it is. She's going to structure the questions in a way that's going to be like, you have all sp2 hybridized and you've got a third degree and a first degree, like, you know, and then you've got a, you know, no resonance, right? Non-resonance stabilized, right? Like it will be something that's like, or like, oh, you know, first degree radical, you know, non-resonance stable, right? Like whatever it is, right? So it's going to be super obvious. So if you can just remember this here, right? Where these things lie, the SP is the furthest down, SP3 is the highest up, right? And, you know, 3 through methyl, if you can just remember those patterns to be able to say, you know, and then wherever your product reactants are and how far up on the product scale, remember that your bond dissociation energy is the difference between those two. If you can just remember this piece of it, the questions, I always say, the homework site is level 1,000, the tests are level 50, right? Like, you know, and it's usually pretty indicative. Her extra credits are usually pretty indicative about what you're going to see on the exams.
Yeah, and this might be just like outside of the scope, but like what we need to understand, it's just like I don't really like memorize things. I more just like try to get the reasoning because then I like don't have to memorize, you know.
Totally.
So I did not understand when she said in the like in the lecture video explaining why a tertiary is more stable because so my understanding was like of tertiary, like, you know, you're bonded to 3 things that aren't hydrogens, right?
Yeah.
And she had said in a previous lecture video that hydrogens being 1s as their atomic orbital have like the best overlap with something like when they're, you know, in a bond and bonded to another atom's atomic orbital, and therefore it's going to be like very strong and very stable. So then if tertiary has the least amount of 1s and hydrogens, I don't understand why that like that's more stable. Like to me, like I thought the pattern should be the other way around, and I just don't know why. I don't know, maybe this is like totally like irrelevant and outside the scope, but like do you have any idea for like how she gets primary, secondary, tertiary in that order for stability?
Let me see. So this would be an example. Oh, I hate drawing out all the hydrogens. This would be an example of your tertiary, right? Versus your methyl. We could even do a first degree, right? And so the hydrogens, you have to kind of think about the hydrogens as like a sidekick. They'll bond, right? Like they'll bond. Oh, did I? Oh no, it's up there. You know, they'll bond to your carbon, but it's not going to do anything for your carbon. Like think about the hydrogens as like, your Pomeranian, right? Like they're there and they're cool and they, keep you company, but they're not going to do anything to help you like pay the bills or, if somebody tries to, mug you at the stop sign, your Pomeranian's not going to do anything to help you, right? But if you had a Mastiff, or if you had a friend, right, another carbon, right, or if you're rooming with somebody, right, another carbon, they're going to help to pay the bills, right? And so hydrogens, and even if you wanted to think about it like the way that you explained it, right? So if I have, whoops, I don't know why it always does that. So if I have this radical here, and then I'm bonded to 3, and then those are bonded to 3, right? It's going to create a more stable structure. Whereas like the radical here, it's bonded to 3 and then that's it. And like the hydrogens, they really don't, they can freely come, freely go. An oxygen can come and steal it at some point. Like they're not really there. They're there for show. They're there to stabilize the structure in the moment, or like to be able to do acid-base reactions, or stuff like that. It's basically, you've got your hydrogen, your hydrides and hydroxyls, and to be able to just basically move electrons around. I hope that kind of makes sense, to just think about hydrogens as like a placeholder and nothing more than that. And so when you have something like this, and a 3rd degree radical that has more friends, think about a hydrogen as a picture of a friend, and think about a carbon or another atom as like the actual friend that's there, right? Like, your group is going to be larger. You're going to have more strength in numbers when you have a real atom as opposed to a picture of an atom, right? Like hydrogen is like a picture of a friend. Hopefully that makes sense.
Thank you.
Yeah, no problem. Let me answer Nicola's question about nomenclature. Okay, so how are the hybrids connected to degrees? This is due to the percentage of S and P, correct? The sp2 and sp3, Nicola, percentage of S and P, yes. Like, so your sp3, excuse me, it has more P? No, more S. Oh God. Yes, it has to do with your percentages. I'm sorry, it's late. I can't remember exactly which. I forget the order, right? Like you can forget the order easily, right? But yeah, more P. Yeah, exactly, because you have more of them, so you would have more P. Yeah, thank you. Versus so you would have more strength in numbers. And then how are the hybridizations connected to the degrees? Do you mean like degrees, like your radicals, like your 1st degree, 2nd degree radicals? Is that what you're talking about? Yeah. So your hybridization, it doesn't really have anything, the carbon atom doesn't necessarily have anything to do. The carbon atom's hybridization doesn't necessarily have anything to do with the radical degree. The radical degree more has to do with like how many other substituents it's connected to. So I mean, I guess you could say it's kind of one and the same, right? So where is it? Like here, right? Like our radical, this is an sp2 hybridized, right? sp2 hybridized, but this radical here would be a first degree radical, because once you put the radical there, it's just sitting on one carbon, versus this is an sp3, or maybe these two would actually be a better example. No, I want to find one that's one and the same. These are okay. These are both sp3. Oh, what just happened? There we go. This is sp3, and this is going to be a first degree radical, because you're just going to have a radical sitting there, right? But we have our two hydrogens here. This is also an sp3, but it's a third degree radical because we have 3 substituents connected to it. Oh yeah, no, you're fine. I get it. I have one kid in bed and the other one watching a movie because my husband's who knows where. So no worries. So hopefully that makes sense. So the hybridization of the carbon atom doesn't really mean as much to the process as where is the radical sitting once you've broken that bond. So this is an example of a third degree, right? And here I drew out the picture. And there's our, right? So this is a third degree radical, versus this one would look like radical right here. So this one. Hopefully that makes sense. Say nothing if you understand. No, I'm just kidding. Okay, perfect. And then nomenclature. Okay, cool. Yeah, I'm teasing. I'm sarcastic, so please don't take it the wrong way. So nomenclature, you said what? Okay, thank you. With nomenclature in ring structures, how do you know what to attach the cyclo to? Can you give me an example? Like, or if you have like a homework question in mind, like for here, cyclopentane, this is like something maybe that you would attach it to, just an FYI, phenyl. I mean, a 6 carbon ring is always known as phenyl. So, but cyclohexyl or whatever. So like for example, this, we have this cycloheptane here, or this cyclopentyl here. Is that what you're talking about? Okay. So in this example, our ring is our main structure. So that's why we have this cycloheptane here at the end. And 1, 2, 3, 4, 5, 6, 7, right? So the heptane is the 7 part, and the cyclo is to identify that the heptane ring, the main structure, is a circle. And then we identify the substituents that come off of it, which are these ones, versus this, if it's a substituent, so the cyclo attaches to the main structure, not necessarily. So for this one, it just depends on what it is you're trying to identify, right? So for this one, the cyclopentyl is actually a substituent. So if your main chain is a ring, you add cyclo to, remember your main chain is identified at the end as to how many carbons are in it. We have, did I put it in here? Yeah. Hex, hept, oct, non, etc., etc. Versus this one is a substituent. So just like how we put our substituents at the beginning of the structure. So annoying. So the cyclopentyl is identifying the substituent that is located on the 1, 2, 3rd carbon. So it just depends on what you're trying to identify. So in this case, our main chain is linear. So that's why we just see heptane, versus in the first example, our main chain is actually that circle, the ring. So that's why the cyclos at the end is not the main chain for the second example. Exactly. So that's why we put because The cyclo just identifies what it is that's in a ring. So in this example, in this second example, our main chain is 7 structures, 7 carbons. So that's where we get the heptane from. That's where we get the heptane from. And then the substituent, this substituent is a cyclopentyl. It's cyclo because it's in a ring structure, and pentyl because it's 5 carbons. And so, and it's on the 3rd carbon of the main heptane chain. So that's why we have 3 dash cyclopentyl dash, etc., etc. Let me know if there's more that I could do to explain that. If you have a question about that in particular.
Can I have a tack on a question to the nomenclature bit?
Yeah, where
Oh,
does the
sorry,
4
she
come
has
from?
one.
No, that's okay. Yeah. So in the second example, the 4, and then yes, you definitely can. So this 4 comes from this 4 here. So 4 methyl is the methyl group right here. Remember that when you just see a line, whatever, say this is a chain, if you just see a line like this, remember that this is just a carbon that has 3 hydrogens attached. So this group is considered a methyl. Remember, methyl is CH3 because it's a chain off the main. Yeah, it's called a substituent because it's a substituent off the main chain. So you use the term main chain to longest chain, main chain, whatever, to identify your initial structure, your heptane in this example, or a cyclopentane in this example. And then you number your chain. Say we have, some substituents here and here, right? So we would choose to number our chain from this direction, 1, 2, 3, 4, 5, 6, right? Or we could do, as I'm sure you guys have seen, 1, 2, 3, 4, 5, 6. We would not number it this way because this would be 4, 5, 6, but then you only have, which this is also 6, right? But then you have to decide how many substituents you have. So if you labeled it this way, 1, 2, 3, with the green, you only have 2 substituents. So green is 2 substituents. Blue or purple is in the same direction, but purple is 1, 2, 3 substituents, right? 1, 2, 3 substituents. So and then blue is also 3 substituents, right? So you always want to do the most. You always want to choose the chain that has the most substituents. So now we're going to decide. Yes, exactly. Sorry, I just read that. Yes, but then you would want the lowest number for your substituents. So that's why we choose blue to go in this direction, because our first substituent shows up on 2 versus if we chose purple, our first one would show up on 3. So I forgot how we got here, but yeah, methyl. So these 2 are methyl groups, and then this would be an ethyl group. So so you would have 2, 4 methyl, and then you would have 2, 4, and then you would have 3 ethyl. And then but when you're naming a structure, you always start alphabetically. That's where we're at right now. So 3, I mean, you always do alphabetical, but there's lots of, or this is, I always forget this part. 2, 4 dimethyl. Don't forget that. It was what I always got wrong on my exams. Dimethyl, and then hex or whatever. Hexane, yeah, because we're still in ane, is the alkane. There's no double bonds. Does that make sense? You, Jackie, I think you had a question on top of it as well.
Yeah.
Nicola, feel
yeah,
free to type in whatever you want to. Yeah, go ahead. When do parentheses come into play? parentheses are typically going to be when you have you seen parentheses? I believe parentheses are typically when you're going to have your like 3S. Like you would have. Oh, do you see parentheses like this sometimes? Can one of you guys confirm that? Yeah. But you don't see them like this, correct? Yeah. I think you would also see them when you get to S and R. You also see them like this. You'll also see Z and E. You'd also see it like this, right? I just want to check in this. So here they don't have parentheses. I'm not sure there's a rule about if you just have numbers that you need to have parentheses. That might be a Dr. Pillai question. I can try to confirm that for you. But I think if you just have numbers, you don't have to have parentheses. But when you start seeing stuff with S, R, or Z and E, you will include parentheses. This might be just a preference thing, but don't quote me on that. Jackie, you want to pop in with your question?
Yeah, I have a question about identifying the longest chain. So this might seem like a really obvious question because I think it's supposed to be, but when I was going through the homework, I got confused.
Yeah.
So, I just want to make sure that you cannot mix a ring and a linear chain. If I can just give you an example, like I just made one up
Yeah.
in my like head.
Yeah.
Say you had a pentane and
Like,
then
not cyclo, right?
oh no, like oh yeah, cyclo, sorry.
1, 2, okay. Cyclopentane. Let me make this a bit. Okay.
Yeah, and then on one of the corners, say you had like 4 carbons in like linear. Yeah, like that.
Mm.
So my question is, you know how in the ring,
would this be cyclo a cyclopentane at the end, or would it be a one dash cyclopentane at the beginning? Is that what you mean? Okay, go ahead. No.
I was just going to ask, when you're trying to find the longest chain, I just wanted to make sure you can't mix a ring and linear, because like,
Oh,
so
no.
technically, because like if you say you started on the linear part and that's 1, 2, 3, 4, 5, and then you could just go into the ring.
Sorry,
You can't do that,
that's
right?
5. Sorry, this is 5. I missed a carbon here. No, your chain's different from your ring. So this would be 5, 4, 3, 2, 1, and then did you say 4 carbon chain? What was it?
Yeah, but whatever.
4
It
carbon?
like it
Yeah, it
doesn't
doesn't matter.
like yeah.
Yeah.
But like
Okay.
I just want to
1,
make sure, like if you're gonna like
5.
say the longest chain is the ring, you cannot go outside of the ring. Like, and if you said your linear is the longest chain, you cannot then go into the ring. Correct? Like, does that make sense? Because like I'm
Like the
trying to
blue that I
basically,
just did? Like the blue?
yeah, that's not
Yeah.
allowed.
No.
Okay.
No, it's always one or the other. It's never both. Okay, just give me a minute. I'll be like 10 more minutes, okay? Oh, thanks so much. I'll just give me like 10 more minutes, okay? I'll be back. Okay. No, take it. No, you can't. So it's either the ring or it's the chain. It's not both. So, trying to see if I have
So
like
the
up
carbon
here,
that's attached
Go ahead.
to the ring and the linear structure, is it one or the other? Does that make sense?
Hang on.
So where you have
this
one,
carbon here,
yep.
that carbon is the ring. Because think of it like this, if
Oh,
you
okay.
didn't have that carbon, it would look like that.
The
Right?
ring wouldn't be
Yeah, the
complete.
ring
Okay.
wouldn't exist. Yeah, exactly. You would have this, and then you would have 1, 2, 3, 4, 5, right? So
So
it has
say the
to,
linear, oh, sorry.
no, go ahead.
Say the linear part was the longer part. So then in this case, just like let's pretend it is. So then in this case, we would say it's a 4-carbon linear, like is the backbone.
Yeah, like,
But it couldn't be because that ring structure is 5.
Yeah, I'm just saying like pretend, okay, fine, like pretend the linear part is 6-carbon, like whatever, like just like pretend it's more. I just want to make sure you're not going to include that circled pink carbon when you're like, you know what I mean?
Yeah, that was what I just asked. So it has to be a part of the circle or the ring.
Y-
Excuse me.
Yeah.
these
Yeah,
these
it's a good
green
point.
dots indicate right potential, like a bond that will be here, right? So those
Okay.
green dots are this right here. So you have to, this top pink circled ring right here has to be a part of the ring, or else it's not a ring. So the
Yeah.
bond that you're creating is between this carbon and this carbon, and these are
Mhm.
separate. These are separate. So you would have, let's just say this kept going right like this, you would have a 1, 2, 3, 4, 5, 6, 7 chain, and a 1, 2, 3, 4. Those are the ink's too big, but hopefully you guys get it. And a 5, a
Then the
cyclopentane.
linear chain would be the main chain.
Yeah, so somebody else asked this um in the discussion board about oh no, that was specifically about a phenyl though. It was about like typically a phenyl will be a substituent. And I added it into the notes just so you guys could see that. Where did I put it? It's this is just specifically talking about a benzene ring. Yeah. So as far as whether or not, like in this case, your heptane, your chain is larger than your ring. But you want to also think about it in terms of, where did I put things? In terms of like what, like this is kind of a bad example for what I'm about to say because there's only one substituent no matter which way you go. But you want to think about it in terms of like substituents as well. So say you had this 1, 2, 3, 4, 5, 6, 7, but then you had this, and then you had this, right? This would have, our pentane ring actually has 3 substituents, whereas this main chain only has 1. It just has this 1 substituent here, right? So that's why we would use cyclopentane as our main chain versus, say we had our cyclopentane, and then we had 1, 2, 3, 4, 5, 6, 7, and then we had a methyl, and then we had an ethyl, and then we had whatever, right? Like, so then we would say that our main chain, because there's 4 substituents off of our main chain, and to clarify that this iso and this cyclo are all off of this number 1 carbon, right? Because we label these, right? So just remember that, right? Because this can get very tricky. This can get very, very tricky. So remember that when we see something like this is 1 and it's right here. This isn't 1, right? So if the carbon is needed to form a ring, it's part of the ring. It's not part of the main chain. So we would label this 1, and this would be part of our pentane ring, right? And so this particular chain, which is denoted in purple, has 1, has 1, 2, 3, 4 substituents. Does that make sense? Whereas this chain, cyclo has 3 substituents, and this chain just has the 1 right there, right? And this pentane here just has the 1 substituent, which is that entire chain, which then breaks off into all these other things. So that's, yeah, just give me a second, please. That's another thing to remember, right? Not only what is the longest, but what is also going to be hold the most amount of substituents. Does that help?
Mhm. Yeah, thanks for going over all this.
Yeah, no problem, no problem. I'll just say practice your, your drawing your rings and your did I not? Are you guys doing that yet? Yeah, you guys are doing it where you're doing like these things, right? You guys are doing these. You guys are at that point.
I don't know. I didn't finish all the material for this
Okay,
week,
okay.
so I don't
No,
know.
no worries, no worries. Yeah. No, I know it's still early in the day. We're still early in the week. Maybe. Yeah, maybe that's. Oh no. Yeah, it's down here. It's the stuff.
I think
Okay.
I don't think it's that far. Yeah, I got more lecture videos to watch.
Yeah, no, it's fine. Yeah, your chair confirmations and stuff. Yeah. Yeah, okay. Well, we can cover that on Saturday. But yeah. Do you guys have any other questions about what we've gone over so far? Yeah, that's how it was for me too. Don't worry about it. Don't stress.
Yeah, because I work during the day, so like I'm yeah, I got some more videos to watch tonight. Just real quick,
Of course.
for resonance, this is like I don't have a specific question like to
Yeah.
show you, but it's just
Sure.
more of like a conceptual thing.
Yeah.
Yeah, I guess I just sometimes I try when I'm moving electrons, I always have the tendency to try to force them into a bond. So like to try to make another double bond, for example, as I'm moving one step at a time. And as I was going through the homework problems, I realized that the resonance structures that I was missing consistently always had like the lone pairs or always had the radicals or whatever. And I was wondering, is there some sort of rules or just like strategy or like best practices to figure out what is reasonable to have a radical on it and what's not? Because like, how do you know if you're just supposed to force the electrons to be like double bonds or if you're supposed to force them into lone electrons?
Are you talking about radicals or lone pairs? A radical is a single electron and a lone pair is 2 electrons.
Well, I guess then I'm talking about a lone pair because it was before we got to hydro or homolytic or whatever. Yeah, it must have been a lone pair. How do you know if you're gonna put a lone pair on like a certain atom or if you're gonna try to force it to double bond?
Yeah, so like for example here, we're like these sorry.
Because I saw a lone pair on like carbon, and I didn't even know that carbon could have it would have like 3 bonds in a lone pair. I didn't even know that that was like a stable configuration. I see lone pairs on like nitrogens and
Like
oxygens,
this?
but like, yeah, how do you know that that's reasonable?
Like if it would, okay, any model, right? Like, so this will happen, but it won't happen for very long. Very quickly, it's going to want to push these back here, which is then going to have to push these over here, which is going to cause right this. I see.
Mhm.
Right. But nitrogen doesn't like to be negative, right? So yeah, you're gonna have to give me a second, sweetie. But nitrogen doesn't like to be negative, it likes to be positive. So this, would be something where like you wouldn't like not, oh, whoops. You're gonna have to give me a second, sweetie. So this would be like, this is fair to say that there would be like this type of structure happening back and forth. But it's not going to be very fond of this. And typically what you would end up seeing this do is it would bond somewhere, not to hydrogen. I just drew a line, but that this would be a very reactive molecule. It doesn't, neither of these situations are particularly comfortable for carbon or nitrogen, right? Versus like if there was an oxygen here. So let's say we did the same thing, but we had an oxygen here. Very happy oxygen. Oxygen's fine with this. Electronegativity, you know? So, yeah. So it's just gonna kind of depend on like what your setup is, right? And if you want to send me, like, if you come across it again, yes, no problem. Yeah. If you want to send me like a particular question that you come across that has an example of like, say, I can't think of one off the top of my head, and I don't want to like tell you something wrong, but like where you maybe would have something like this, and it's like, well, how do you know when you're gonna do this and like push these here versus push these here, correct?
Yeah.
Like, is that kind of what you're talking about? Yeah. See if you
Just
can
like,
find a question. See if you can find
yeah.
a question for me, and I'll explain it to you, but I don't necessarily want to set up a question because I don't want to set it up wrong. And so I would feel more comfortable being able to answer your question with like one that was already set up.
Yeah.
So that I could show you how it works, if that makes sense.
Yeah, no, I appreciate that. Yeah, so I like did these problems like a few days ago, so I don't have like I didn't pick one
Yeah.
out, but like it was just like in general, like well, because in the lecture videos they were even saying like, oh, be careful to like, not draw too many arrows to go step by step. And I always draw too many arrows, and like and then I get the last resonance structure in the list and I like forget all the intermediate ones. And like a lot of the times the intermediate ones had the lone pairs on like the central carbon or something. And I don't know, I was always just trying to force double bonds to the point of like forgetting about the lone pairs. So I'll have to like look again and get it. I might have it for Saturday. That could be.
Okay. Yeah, that sounds good. And and just double check. I have to hop off. I gotta take care of her. But just double check that, like, resonance contributors question number 3, if that's something that is similar to what you're talking about. And I'll make sure that either I'll make like a short little video and send it to you, or we can kind of address it when we hop on Saturday or whatever you want. So
Thank you. And thank you for all the time. You're great. Very helpful.
No problem. Anytime. I will. I remembered to record, so I will upload these this time.
Thank you.
You're welcome. Have an amazing night.
Yeah, you too.
Thanks.
All right, bye.
Bye.